Hello community! We have a new RAG system and this one is really interesting. It is about a hierarchical reasoning on a GraphRAG structure, so we will work here with knowledge graph. So if you have here just simplification here of a graph structure and you are interested here to have here a deeper reasoning structure, you immediately see the problem. Imagine this is a three-dimensional sphere and it is about, I don't know, astrophysics. So all the heavy objects like galaxy formation or star formation will be here on one segment, and maybe everything that is connected with very light particles, maybe elementary particles, will be at a distant region here in our knowledge graph. And now the problem is, if you have some deep reasoning, maybe you need to have the connection, even in astrophysics, and let's say very shortly after the Big Bang at the inflationary phase, you have to understand elementary particle physics to understand how the cosmos was expanding. So you see, you need extreme different complexity levels, and you can do this normally not on a flat knowledge graph. Now the idea is to have here filters that you look on this graph. But filters are not really helpful. We have really to actively manipulate the data here in a new other form, another representation here of the data on the knowledge graph. And this is HiRAG. So let's have a look at this. If you want, think of it like generating different slices here or different filters of the complexity of a knowledge graph in a high-dimensional mathematical space. HiRAG, retrieval-augmented generation with an hierarchical knowledge here. Really interesting. I'm talking here about end of June 2025. This is here from the Department of Computer Science and Engineering, the Chinese University of Hong Kong. Now, you know, in my last video, we talked about LeanRAG. And LeanRAG is even more complex. And LeanRAG is really here co-designing here a knowledge graph. HiRAG is real close, but a different variant. So if you understand LeanRAG, you will find that HiRAG is real simple, especially in my explanation. So let's have a look here at the overall architecture. We have, again, like in LeanRAG, two main bodies that we have to look at. At first, we have a pile of documents. This is our PDF or our internet or a SQL, whatever you have. And then we go to work. So you see, we have at first the HiIndex, the hierarchical index building, and then the HiRetrieval, the hierarchical retrieval here of our data. Now, careful. You do see here different levels. And I made the mistake that I thought reading the paper that those levels are somehow connected in a simple way. Turns out they are connected, but not in a simple way, so I will explain it in detail. Of course, we have different layers, and let's start here with the first one. Let's say we have here 10 papers here on, I don't know, general relativity. And let's say we have here the chunking, we have our tokenize and prepare that input here. And let's say we have 300 chunks that we have to operate on. And after an entity extraction that we have on this particular data stream, let's say we identify here for general relativity about 520 unique entities. So let's start now with the HiIndex run with this construct here. We have here a layer 0. This is here the normal layer where we have our, let's say, 520 entities. And now, you know from the last video, we need here a Gaussian mixture model. And this is doing here the cluster for elliptic or any other form here of a graph clustering methodology. And let's say those 520 entities on the layer 0 create about 40 thematic clusters here in our general relativity paper. Now what we do, we build now summary nodes from those 40 clusters. Now each cluster becomes now in the next level here a summary node in itself. This is now created by a very powerful LLM that has a deep domain knowledge and a deep reasoning. So therefore this LLM is able to build here the next layer, layer number 1. And then we go into a repeat cycle. Of course, you remember we have to have here similarity measures calculated, and therefore we still go here that we do here a complete embedding of the nodes and of the edges. I will leave this out because this is a standard procedure. I will explain here the real core of the mechanism. So we have to have here a vector operation. We have to generate here embeddings. We'll compute this with an SBERT model, whatever you like. Off-the-shelf SBERT is just great. And then we see there's another clustering emerging here at level number 2 on a higher complexity level. And let's say now this LLM here, it's a real powerful LLM, let's say it's GPT-5 Pro or whatever, finds now 6 thematic clusters here of those particular summaries, of those 40 summary nodes. So you see now we can create layer 2. So you see here, this goes now on. Given here that general relativity has maybe more than 2 layers, but let's stay here in a simple case. Layer 2 has 6 higher summaries, compact object, cosmological solutions, whatsoever. And let's say we have an epsilon of 5% spread, then we have a stop condition. Therefore, we have here 2 layers. No, layer 0, layer 1, and layer 2. So we have the normal entities. We have then the summary entities, and then if you want here the meta summary entities, and you clearly see how we build here our indexing of the hierarchical knowledge layers. Great. Now comes the interesting part. Now in this HiIndex run, we have a community detection. And now interesting, we use here the Leiden algorithm, and now we go over all the different layers. And don't mix this up. This is now here the core insight. This is the beauty that you have here if you want here a cross-cut across layer 0, layer 1, and layer 2. And with the Leiden algorithm, let's say we find 8 communities. So let's say we find a community, there's a specific data information about compact stellar objects and gravitational wave signatures, if we stick to astrophysics, no? In the scientific literature, this was the topic that they researched, and this is the topic that is current, the research topic here of our little planet. And then comes now the query. After we have, let's say, redesigned here the data availability here to a particular pattern for this HiRAG system, I have now my query. The human query comes in and says, hey, do you exact solutions here, Schwarzschild or Kerr solutions, shape here the gravitational wave ring down signatures? So you see, astrophysics, no problem. And now we come to the second part. So my query here comes in here, beautiful. And now something happening. Now you understand, if we want to have here above the flattened knowledge graph, we need to have, again, hierarchical structures. So again, we will work with multiple, let's say, I don't want to call it here a level, let's call it hyperplanes. So at first, we have that we say, okay, we have local entities, yeah? Like the Kerr metric or the Schwarzschild metric, the ring down, the quasi-normal modes, or the black hole spin features that we have. And then we have communities. Just to make you familiar with the terms, I explain the details of the term a little bit later. So we have a community A. This is, for example, as I just showed you, compact objects and gravitational wave dynamics. Or community B is pure mathematical solutions for whatever. So here we have global. This is here global, entities. And then key entities per community. We identify those, we compute here, the AI computes here the shortest path, let's say between the Kerr metric and the quasi-normal modes here, given here the information here of this extended knowledge graph. And therefore we build now bridges. And we build bridges between the local level, the detail level, and the global level. So the bridges are now, guess what, triplets. And they include, exactly like you imagine, the Kerr metric. So here an element from the local community determines, and one element here, quasi-normal mode spectrum, or whatever you have. Now the beauty is that those bridge triplets now, they form now our reasoning paths. So we are not depending here on the parametric knowledge of the LLM itself for the RAG reasoning path chain of sort, but we have it here predefined in the structured data representation of our knowledge, given that we went here with this step here, these 2 HiRAG systems here, and the second part, the HiRetrieval, this provides us here the reasoning path. This reduces all the hallucination, hopefully. I will show you the result in some minutes. And we have really fact-based reasoning paths that are within the body of knowledge that is available here to this AI system, agentic system. So you see, this gets interesting now, huh? Let's have a closer look. Let's look at the complete flow here of both elements, no? So at first we have our documents and we chunk our documents and we have somewhere a store. So what we do is we have now the entity extraction via an LLM, and we have the relation extraction that we know from the classical knowledge graphs, no? And now the relation extraction build now a base knowledge graph layer, let's call it G0. And plus we have now the computer embedding for all the nodes, beautiful. And then we're already here at HiIndex. We run here the first HiIndex loop, so we have a clustering algorithm here, Gaussian mixture, or I told you in my last one, dbScan is an option or whatever you like. So the LLM is now summarizing here the thematic scientific cluster. Add now summary nodes here and updates, of course, not only the nodes in a new layer, but of course we also have to calculate here the embedding within the same S-BERT model, hopefully, until we reach here. We continue here building layer and layer until we reach here an absolute threshold, let's say, of 5% difference. Then we use here a Leitner algorithm here on GK. We generate here then on those levels community reports. I mean, we, the LLM, of course. Again, we have to create vector index here over the top layer nodes. Okay. And then we come here to the HiRetrieval phase. Again, we have unfortunately to embed the query because we will have to calculate the similarity of the query with all the elements here of our hierarchical structure, but okay. So we find now the top n local nodes. We get the communities. We have then the top m keys here. We can calculate the shortest path and we can collect here the bridge triplets that will form here our fact-based from the knowledge graph determined reasoning paths, the reasoning traces. And it's not here that the inherent parametric knowledge of the LLM defines somehow or hallucinate reasoning traces. Those are really fact-based on the knowledge graph. And then we compose here the final LLM prompt, of course. We are here in a RAG system after all. So what we can provide? We can provide the global reports. We can provide the bridge triplets here for the reasoning paths. We can provide the information from the local hyperplane snippets. And this is now the perfect if you want context engineering, or prompt engineering, whatever you prefer. And we can generate now an answer by an LLM since it has now all this information here from the high complexity level to the medium complexity level to the low complexity level with our bridge triplets that form out here the reasoning traces. That's it. Summary. So again, maybe we have those layers here in the first part from the HiIndex phase. So what we do, the hierarchical index construction. No? So layer 0, the base entities extracted directly from the text, like the technical term Schwarzschild metric or Einstein field equation. Then we build the layer 1. LLM builds the layer 1 here in our example. It creates summary entities here by clustering here particular layer 0 nodes. Like say, 10 nodes here from the layer 0. So we have now the summary entity is called exact solution to Einstein's field equation. And then we have maybe a layer 2, even a higher summary. So we're abstracting now the layer 1 clusters. And instead here of the exact solution to Einstein's field equation, we have now classes for general relativity solutions in general here for different forms of geometry and of the spacetime and so on. Until the cluster sparsity CS is now below the 5% threshold or whatever you define, whatever parameter you define for your system. This is here the essential parameter when we say, okay, now it's enough. Now we can stop this. So if you want, the layers now in these examples are the vertical abstraction axis. No? Each higher layer compresses now, or if you want, abstracts here, the layer below via a summarization that is performed by the LLM. Second part then is here the retrieval. And as I told you, we have also here 3 steps. I'm not saying that we have 3 layers. 3 steps here. So we have at first the local entities here of the lower hyperplane, to the communities, and then the global. So let's look at the first term, the local entities. Again, just a repeat. This is not a layer 0 specific, but rather a very similar entity selected here from the top layer of the hierarchy. And you might say, why? Why is it not here on the middle layer or the lowest layer? No? Why is it from the top? Because think about it. We have these aggregation reports, these higher abstraction reports written by the LLM. Therefore, on the top layer, this will include all the knowledge and information about both the base entities and all other summaries. So we have now, if you want here, the retrieval can catch now both the fine-grained information nodes and the more abstract nodes. For example, if I have a query, how do black holes produce gravitational waves? The local set might include now here information epsilons here, layers here, from all the different layers. So from the entity layer 0, we have parametric. From the layer 1, we have the exact solution to Einstein's equation. And from the layer 2, the highest, if you want, complexity layer, we have compact objects. So you see, we don't lose here the high-level abstraction to the low-level abstraction connection. Great. Communities here, the second part. After we built here all the full hierarchical knowledge graph representation, we'll run now here the Leiden algorithm for the community detection across all layers. Please, this is important. Across all the layers. So these communities, if you want, are now the horizontal groupings of the related thematic nodes. And again, you can mix all the layers from 0, 1, and 2, all the different nodes. No? And now here's an example. The community might contain here Schwarzschild metric here from the lowest layer, the Kerr metric also from the lowest layer, then the exact solution from layer 1 and compact object from layer 2. So horizontal groupings, each community has written also a report called in the paper the global context. So you see, we keep pace here, and we have here drop down a hierarchical reasoning structure with reasoning traces established. But those are established by an LLM, so you depend on the factual understanding, on the domain knowledge, and on the reasoning capabilities of this LLM that builds this representation for the RAG system. Okay, and then the last one here, the global one, this bridges, connects the global and the local entities, is not a layer or a community by itself, but think of it as a subgraph, a complex subgraph you extract, add a query here at inference time by linking here the key entities from all the communities. So this is done by the shortest path. Let's say you want to find here the shortest path between Einstein field equation and space-time curvature. Guess what? This goes here to gravitational lensing. Field equation, space-time curvature. Gravitational lensing is then an effect of curvature. And then you have further effects. So if you want it here completely abstracted here, the layers in HiRAG are carefully structural, built offline with a HiIndex methodology. The communities are overlapping groups on the hierarchical knowledge graph, also built and discovered offline with the Leiden algorithm. And then this local, global, and bridge views are the retrieval views per se here in the retrieval phase. They are assembled online with the HiRetrieval methodology that we just talked about by now selecting from all the layers and all the communities here very specifically. So this you have, if you code it, really to be careful that you get it right. If you wanted here another example, let's take one from physics, pure coincidence. The layers are like the scales of the description. The layers are here for the microscopic level, the mesoscopic level, and the macroscopic level. The communities are more subsystem or ensembles. So we have here the atoms as a community, the molecular structures as a community, or bulk properties as communities. This depends here on, let's call it, the intelligence of the LLM and the understanding, the world model of the LLM, how it structures now the communities. And then finally, the retrieval use. We have local, global, bridge. You use when answering here a very specific question, and you have, if you want, 3 different views. The detail measurement in physics, this is what we call here the local view. The overall system description would be the global view, and linking now the equation between the local and the global structures are the bridge view. So rather simple, but somehow in this paper it's a little bit of a complex representation. Layers, vertical abstraction layers, communities cut across the layers, and retrieval view could be slices. That's it. Now, what about the result of this methodology after it took us so long to really understand what we are talking about here and what is the difference here to the other methodologies? You can say the local snippets and the global reports, they really live at different abstraction levels here. And therefore, this bridge view, these bridges force here really consistent, the triplets here, a multi-scale reasoning and traces and the reduce here also the contradiction and the hallucination. Yeah, here you have now the result, and as you see here for all the different mix and here different benchmark and here the different parameters, you have the naive RAG, the HiRAG, and you see HiRAG underscore is here the best performer. HiRAG is here just beautiful. What a coincidence. Now you see here we have now the GitHub repo of HiRAG, beautiful. It is an active repo. You see just 2 days ago here, especially HiSearch for DeepSeek or HiSearch GLM. They use here DeepSeek versions 3 and GLM 4.5 here, especially real nice implementation, I think, real nice models that they have implemented here. But you know, the big question is, if they work on a scientific topic, if they work in theoretical physics or astrophysics, where we have that the LLMs are understanding what is astrophysics, where I have to place the complexity levels and what elements I have to place. But if you go in something a little bit more non-scientific, you know, more open-ended, I would be highly interested if you work with this. Have you experience with HiRAG? In what domain are you working? And you find that HiRAG is the best model here that goes beyond GraphRAG? Or would you rather go here with this hyper-GraphRAG implementation, or would you choose any other RAG 3.0 implementation here, multi-agent implementation? What are the particular strengths here of HiRAG in the real-world application? If you have some experiment, if you have some feedback, I'm looking forward to it. And if not, I see you in my next video.